Hi, I am Naresh. I will be presenting our ICML 2023 paper, Multitask Structural Learning using Local Task Similarity Induced Neuron Creation and Removal, a joint work with Baram Zunos and Elahe Arani. A prominent approach is to train neural networks that can perform a single task. On the contrary, training a neural network to learn multiple tasks has notable advantages like improved inference speed and memory and improved information sharing between tasks. If this shared information is complementary, it can improve all tasks. However, if it is conflicting, task interference occurs which leads to accuracy drop. Existing works have attempted to reduce task interference in a number of ways, including task grouping, loss balancing, partition strategies, input-dependent dynamic architectures, and learning the branching structure. In learning the branching structure, the goal is to identify where each task can be branched to minimize task interference while maximizing complementary information sharing. Most methods that learn the branching structure after learning the architecture require an additional retraining step to train the weights. However, in the brain, both the neuronal structure and the synaptic weights are learned simultaneously. Using structural learning operators could bring improvements to MTL. Structural learning operators include neuron creation, where new neurons are created based on local activity, neuron removal, where redundant neurons from a dense set of neurons are removed, synaptogenesis, where new synaptic connections are created, and synaptic pruning, where existing synaptic connections are removed. MTSL uses neuron creation and neuron removal. MTSL begins initially with each task having its own network. The first layer in a task network is called a task node. During the task learning phase, the objective is to minimize task losses and to align the output features of task nodes by increasing their similarity. After a set number of epochs, MTSL moves to the structural learning phase. This phase begins with neuron creation and then moves to neuron removal. In neuron creation, the task nodes that result in similar features are grouped together. For each group of tasks, a group node is created. The knowledge from the grouped task nodes are transferred to the corresponding group node. In neuron removal, the redundant task nodes that have already transferred their knowledge to a group node are removed. The remaining layers in the task network now branch from the corresponding group node. After the structural learning phase, MTSL moves back to the task learning phase. After alternating between these phases for a set number of times, MTSL moves to a fine-tuning phase where only the task losses are minimized. Here we compare the performance of MTSL against various state-of-the-art methods. LTB and BMTAS are two other methods that also learn the branching structure. In the bottom three rows, we see that these methods lag significantly behind MTSL as these methods do not learn the optimal weights when learning the architecture. However, after retraining, the middle rows we see that LTBR and BMTASR attain multitask performance close to MTSL. Notably, MTSL also learns a more inference-efficient architecture. We evaluate MTSL additionally on UniNet and learn the branching structure in both the encoder and the decoder. The first baseline is OneNet, which naively combines all encoder and decoder layers. The second baseline STN has a single network for each task. We see that MTSL results in a network that is closer to STN in multitask performance while being closer to OneNet in inference efficiency. We also evaluate the robustness of MTSL to different types of image corruptions. Overall, we see that MTSL leads to a resultant architecture that is more robust across both datasets. When using the deep lab based architecture, we see that MTSL leads to more inference efficient architecture. In UniNet, MTSL results in different converged architectures based on the dataset. Inherent biases in the dataset affect the task groupings, leading to different architectures. Nevertheless, MTSL leads to architectures that have inference efficiency closer to OneNet. Inspired by the brain, MTSL brings structural learning to MTL with two neural operators, neuron creation and neuron removal. Using neuron creation, MTSL transfers the features of similar task nodes to the created group node. Using neuron removal, the redundant task nodes are removed. MTSL learns both the branching structure and the associated weights simultaneously. MTSL leads to improved robustness and generalization. As future work, switching to the structural learning phase could be done automatically based on interneuron activity. Two additional neural operators, synaptogenesis and synaptic pruning, could be used. Thank you.